We are Aquavolt, and welcome to our preliminary design presentation. To start us off, we're going to get right into our problem statement. Outdoor campers just often lack reliable power, making it too hard to just keep essential devices charged sometimes. Solar panels depend on weather, and our battery banks are just heavy and they may drain quickly, creating safety risks. Our solution to this is going to be a compact micro hydro turbine that uses stream flow to generate stable USB power. And then the goal to this will be a lightweight, durable, easy to use, renewable charger that's going to keep our users safe and connected off the grid. This then leads us into who our primary target is. These people are our outdoor enthusiasts who can't backpack, hike, or spend extended time in off-grid environments that just need a reliable way to charge our essential devices. More specifically, this is going to include our backpackers and campers who want lightweight portable power solutions, survivalists and preparedness users who need dependable off-grid energy for emergency communication, fishermen, hunters, and adventure travelers who all operate near heavy rivers or streams and everything like that, international travelers or remote field researchers working in areas with just limited electricity, and then disaster preparedness communities seeking renewable backup power options. Now, you might ask yourself, why are these our ideal customers? And let me tell you, they regularly experience situations where traditional power sources like our solar panels, battery banks, and fuel generators are just unreliable, heavy, or weather dependent, thus making a portable micro hydro charger extremely valuable. Unfortunately, we do have some competition. The water lily turbine, as you can see in the bottom right of the corner. Right now, they're designed for camping, kayaking, and backcountry travel, but so are we.
Now let's take a look at some of the voices from our survey. Meet Jason, Daniel, and Anthony. Jason is a very avid hunter and survivalist. Daniel is a very avid camper, and Anthony is more of a beginner camper. The main question that we asked Jason was, why do you think this product would be helpful to you? And his answer was, when out camping, I hate having to fill up my backpack with multiple different battery packs to attempt to keep all my electric charge. It would be amazing to just have a more reliable rechargeable battery, which our product would be very helpful for this so that he can only have one battery that he has to bring, just sets it in the river, and then he can charge all of the electronics he needs. And the main question we took away from Daniel is, what do you believe would set us apart from other solutions? Where he responded with, often on very cloudy or foggy days while I'm out camping, my solar batteries are rendered useless and my electronics can't be charged, and your product wouldn't be hindered by that. So Daniel found it really helpful that our product would be able to be used in any time of day, whether it be, night, super foggy, where he usually relies on a solar battery. And finally, we have Anthony, where since he's more of a beginner camper, we asked him what has been keeping you from, exploring more of the outdoors and getting more into camping. And he responded with, I love the outdoors, but has been afraid to try much off of the grid camping because he fears that his phone would die and wouldn't be able to contact anyone in case of an emergency. Our product would be very helpful for this because now he will always have a reliable battery for his phone so that he can always reach out to someone in case of that emergency. Now let's take a look at our requirements and target goals. This first goal is we really want it to be low cost, and we feel that a good target for that should be that it should cost less than $900 for a production of 100 units. And then our second really big target goal is to make sure that it's lightweight so that our consumers can make sure that they're, not having to lug a big pack out when they're camping, that they can, still keep a nice weight. And this, we want it to be less than 20 pounds. The third big target goal we have is that it should be easy to set up so that in case of emergency, that can be set up quickly and that you have your reliable energy. And our goal is to make sure that it should take less than 3 minutes to set up. Our fourth big requirement is durability. Since it's going to be in a stream, it's going to have a lot of forces acting on it at all times. We want the product to be able to withstand at least 50 hours of continuous use. And finally, we have reliability, that being a big issue because if it's not reliable, people aren't going to want to use it. And we want to make sure that our consumers have that energy that they need. So we think that the product should always be able to produce at least 5 watts.
This is our conceptual drawing. We had two designs for this drawing. We had one that resembled the water lily, which had tethers and strings to keep it fixed in the place, and a fine mesh to not damage the propeller. For our second design, we extended the tube, added an anchor, and changed the design of the turbine to, to create even more power. For our functional block diagram, we basically water has to intake come through the intake, then through the mesh debris to the generator, which changes mechanical energy to electrical energy, which energy is then stored into battery packs using a BMS to do it safely. Then the BMS will have USB ports such as Type A and Type C to be able to charge our devices. And then the wire loop apparatus. And for all the electronics that we will need, we will use a DC-DC converter to change voltages, such as change 12 volts to 5 volts, or either or. The system controller, LEDs to know the status of whether the device is charging, or even if it's working, and protection circuits to know that the lithium batteries not explode or damage with the water or the electronics itself. For our control system diagram, well, we'll use a mesh to prevent the debris from damaging the propeller and damaging the devices. Then the water enters through the nozzle. Then the turbine blades are used to change the flow stream into rotational velocity. Then the shaft will go into a generator, which the generator is connected to a BMS, which the BMS is connected to the battery. And then we'll have cables transferring the electrical power from the BMS to the battery. We will have a pad eye, so we could attach the tethers to keep the device fixed. We decided to use the motor PMDC 6142K53. Then from there, the motor controller. Then we will integrate it to the
Our
BMS.
design process, it starts with our basic conceptual drawings, which we just went over, and those basic conceptual drawings help flesh out our block and control system diagrams. And we iterated upon this, and with more meetings with the SMT shop, we landed on a final design which incorporates a funnel tube design, a ringed turbine blade, and a fixed motor and electrical housing for rigidity. The SMT shop also gave us insight into material choices and costs of manufacturing. So we are going to go with sheet metal for the funnel tube design. We will most likely print the ringed turbine blade out of a glass reinforced ABS plastic. That's for ease of manufacturing and for the strength and rigidity needed in that turbine blade. And then our original design was a motor and electrical housing, which had screws holding each side. But with our previous presentation and the meeting with the Senti group, we realized it would be much simpler and much more rigid, and just simpler for the consumer if that housing was just fixed by different, components which are either glued or melted in, and it's just permanently fixed and very rigid. Next, for our assembly, we have component one, which is the tube with that funnel design, as well as the holes on the outside to let water flow out easier. The reason why we have the funnel design is to maximize speed of water to try to increase power output. Our second component is the turbine. As you can see, it has that ring on it for more rigidity. It is what's going to power our motor. And then part three is the electrical housing. That's where we're going to have our motor, our battery, and our indicator light to see, charge and any other indications that we will need. And then part four at the very end there with that handle is going to be the cap for the electrical housing. Obviously, it'll be waterproof, and it'll be easy to access from our consumers to be able to modify anything or quickly fix or diagnose any problems within the electrical housing.
Hello, so here are the component drawings. We have a few of the components that we're seeing in our assembly. So for example, we have the the tube for our design. We have our ring turbine. We also have the cap for the electrical housing, and we also have the compartment in which we're planning to put every electrical component. From these CAD drawings, of course, we have dimensions. For example, for the tube, we have relevant diameters as well as like the angle at which the exit is gonna be like inclined. We also have like the ring turbine dimensions. And basically what these drawings are gonna help do is that when it becomes time to make these parts at the lab, it's gonna help us to actually, have like something to follow, something to like designed by. And so these drawings are actually going to be really helpful in the future. So basically, we've only stuck to the static structural analysis, and we mainly just simulated like different pressure loads that we expect our turbine to be going through. And I also just want to mention that specifically we chose the turbine because we do believe it's one of the most sensitive components. It's going to be the one that's going to be under a lot of stress from the flowing water. And it's also going to be our means of generating electricity. So of course, when we have the turbine spinning, that's when we're gonna, get our useful electricity out of it in order to charge our devices. And so we did a stress test on ANSYS. Specifically, this test focused on simulating, like I said, like the pressure loading, and we focused on material choice. So we simulated ABS plastic. We also simulated aluminum, as well as structural steel, just to get like a feel of how different materials are going to perform. And so we just want to share how the ABS plastic did. So on this top image right here, we see that the deformation maximum deformation was only about 0.0345 88 inches, which is actually really small. And so we're not expecting a lot of deformation, which is, of course, a really good thing. We also have an equivalent stress diagram, which is basically comparing our loading stress and finding the von Mises stress, which we compare to the yield strength of the material, and it is well below the yield strength of the ABS plastic. So we do not expect this material to fail for a turbine.
For our motor selection, we conducted a trade study analysis to make sure we chose the most suitable option for our device. We started with a pool of 7 different motors and evaluated them using key criteria that were important to our system, such as low RPM output, efficiency, waterproofing, cost, and startup torque, or low drag. Each criterion was weighted based on its importance, and we scored every motor according to its specifications. Once we totaled the scores, 3 motors emerged as the top contenders, all ranking very closely. At that point, our team reviewed the remaining options in more detail and made a collective decision. We ultimately selected the PMDC K53 motor. Even though it didn't receive the highest technical score in the trade study, we felt it provided the best balance of performance for our needs. Its strong, low RPM performance, solid efficiency, and alignment with our system requirements made it the most practical choice moving forward.
Looking at our budget for the year, we had a total of $900 to spend. So on the right here, we have a table of all the different components that we're going to need as well as materials. So you can see we have power generation, which is going to be batteries and motors. We have the PVC and aluminum and sealants we're going to use, our mechanical components for converting from that turbine to the motor or generator, and then mesh for filtration. We've also included a contingency as well as a category for testing and tools. So any money we would need to spend to conduct testing or data kind of collection in our testing, prototyping, things like that are kind of accounted for there. The total comes out to $420. So this obviously puts us in under half of our budget. We thought this was important because this gives us a lot of money as a safety net in case things go wrong, in case there's issues acquiring one component and we need to switch, in case for whatever reason, something breaks down and we need that money as a safety net. We have $480 left. So this is all estimated based off of prices that we found online from places like McMaster-Carr to Amazon to Ace Hardware. So while these are rough estimates, we believe it is an accurate representation of the money that we will spend. And you can kind of see a breakdown in that table of the percentage of our budget that we're using on each of these items.
All right, so for project management, we have these 2 tables that demonstrate everything we have done from the very beginning of the semester when it came to team charter, team formation, figuring out what we were doing, all the way to now where we completed our CAD presentation last week and have already began working on our preliminary design report. So, project management. We have found this semester to be challenging, especially when it comes to figuring out who's going to do what. But the key to our success has been communication. Every week we have text in our group chat every day saying, hey, who wants to do this? Who wants to do that? Making sure everyone does what they want to do and what they don't want to do, especially when it comes to their skills, as we have some people that are really good at CAD and some people that don't even have CAD installed. But making sure everyone has something set to do for that week it has been a challenge, but we have found success in communicating, and for that have found success overall for this semester. So yeah, we plan to take that into next semester, which is the segue into what we're doing next semester. We're going to be starting the very beginning of next semester, making sure we front load our design, get any finalizations, any kinks out, and then start ordering. We're going to order probably over Christmas break, but that's for the big items because we know there is some time that takes in between getting items and putting it into our assembly. But then we're going to move on to fabrication, assembly, bench tests, and flow tests through the latter half of the semester, making sure we save those final weeks for iteration, reliability checks, and demo-ready finalizations, making sure that our final project is what we want to be and it's set to our standards that we have set this semester. So that is project management. Thank you.
All right, to conclude, all of our design work, user feedback, and simulation results show that Aquavolt is on a strong path forward to become a reliable microhydro charger. Our funnel tube, ringed turbine, and fixed motor housing gives a solid foundation to meet our goals: durability, reliability, and consistent power output. Based on this progress, we recommend moving forward with full prototyping. Our next steps will focus on CFD and fatigue testing, refining the blade and housing geometry, and validating performance in real-world flow conditions. With these upcoming improvements, Aquavolt is well positioned to become a lightweight, dependable, off-grid power solution for outdoor users. Thank you guys, and if you have any questions, feel free to reach out.